Welcome to the Educational Series Part 1 on how to control an inverted pendulum. If you are new to the topic, I highly suggest watching Part 0, where we go through the simpler examples giving an intro to code and math related to the topic. In this video, we will start with a free body diagram and develop a nonlinear system model that captures the inverted pendulum motion. First, let's go through the derivation of the mathematical system model using Lagrange equation of motion. Our system consists of two bodies, cart of mass uppercase m and ball of mass lowercase m. The ball is attached to the cart with a pendulum arm of length L. We have three possible motions, in x direction, y direction, and theta, which is a relative position of the ball with respect to cart. The only force, which we also call our input, is applied to the cart, and that is the only way we are going to control the system. On the left, you can see general formula for Lagrange equation of motion, which describes the total energy of the system. Lagrange is one of the ways to derive a mathematical system model, and it is the one we will be using today. Do not worry too much if you do not understand each term right away. As we go deeper into the derivation, everything should start falling into places. Lagrange equation is dependent on kinetic, potential, and dissipated energies, where dissipated energy is the energy that is lost due to friction. It also has these lowercase q and uppercase q terms. Lowercase q is our generalized coordinate that describe our object's positions. We need coordinate x to show where the cart is located, so q1 will be x. And to know the ball position, we will need theta, so q2 will be theta. Since we have two coordinates q1 and q2, we will also have two Lagrange equations. Uppercase Q is input or force applied to the system. These are the forces that are directly applied to affect our generalized coordinates. So looking back at our free body diagram, we control x position with force U. Therefore, our uppercase Q1 is equal to U. And since no force is applied directly to the pendulum arm to affect theta, uppercase Q2 is equal to 0. Please note that a dot above lowercase q means that it is a derivative with respect to time. For example, x position derivative with respect to time is equal to the velocity in x direction. Theta dot is the change of the angle theta over time, meaning it is angular velocity. We will start by defining positions of the objects. As we said previously, our generalized coordinates are x and theta. The cart position is very simple. Since it can only move in x direction, it is dependent only on x. The ball position is dependent on both theta and x. If the cart moves, the ball has to move with it. Instead of using theta and x, we are going to describe the absolute xy position of the ball, denoted by x subscript lowercase m and y subscript lowercase m. xm is equal to x plus length L times sine of theta, ym equals L plus L times cosine of theta. We also need to find the derivatives with respect to time. Using the chain rule, we can find that x dot m equals x dot plus L times theta dot times cosine of theta. Y dot m is equal to negative L times theta dot times sine of theta. Next, we're going to find the energies. Total kinetic energy is a sum of the cart and ball kinetic energies, which equals to 1/2 times cart mass m times x dot squared plus 1/2 m times the sum of the ball velocities in x and y directions. Substituting the ball positions and simplifying the equation, we get that the total kinetic energy equals 1/2 x dot squared times the sum of masses plus mx dot L theta dot times cosine theta plus 1/2 ml squared times theta dot squared. Total potential energy is also equal to the sum of the cart and ball potential energies. However, because the cart can only move in x direction, its potential energy is 0. Total potential energy equals to m times gravitational acceleration, g times y position of the ball. Note that when theta equals 0, pendulum is pointing up, and when theta is 180, the pendulum is pointing down. Total dissipated energy is described as the sum of frictions experienced by the cart and ball. We are using nonlinear viscous friction, where B subscript m is just a coefficient. Now that we have energies, we are going to take their derivatives relative to the generalized coordinates and construct our Lagrange equations. Lagrange terms relative to x are shown in blue, and relative to theta are shown in orange. First, partial derivative of kinetic energy with respect to x dot equals to x dot times sum of masses plus ml theta dot times cosine theta. Then we need to derive it relative to time. And we get x double dot times sum of masses plus ml theta double dot times cosine theta minus ml theta dot squared times sine of theta. Terms with double dot describe acceleration. X double dot is the acceleration in x direction, and theta double dot is the angular acceleration. Kinetic energy derivative with respect to x is 0, since kinetic energy is independent of position. Dissipated energy equals to the friction coefficient Bm times x dot. And lastly, potential energy derivative with respect to x is 0. We do similar derivatives for the energies with respect to theta, and get the following equations. Now that we have all the terms, we can put them back into the Lagrange equations. Relative to x, we get x double dot times sum of masses plus ml theta double dot times cosine theta minus ml theta dot squared times sine theta plus bmx dot all equal to u, which is the force applied to the cart. Relative to theta, we get mx double dot L times cosine theta plus ml squared times theta double dot plus bm theta dot minus mgl times sine of theta, and all equal to 0, since no force is directly applied to the pendulum arm. If we take a closer look, we can notice that both x double dot and theta double dot are present in both equations. Our final goal is isolating these two terms, and we do not want one of them be described in terms of the other one. So we first are going to rewrite our equations to isolate x double dot and theta double dot. Next, we replace theta double dot in the Lagrange equation relative to x, and we get the following equation. X double dot is equal to Lu plus Bm theta dot times cosine theta minus MLG sine theta times cosine theta plus ML squared theta dot squared times sine theta minus BML times X dot all over L times M plus M minus M cosine theta squared. And similarly, we substitute x double dot in the Lagrange equation relative to theta, and we get the following equation. Good. Now we know how to mathematically describe accelerations x double dot and theta double dot. And as you may have already noticed, these equations are nonlinear, meaning they are very hard to control. In the next part, we are going to go over the linearization of the inverted pendulum and what problems you might encounter with it.